Evaluate each of the limits. A. The limit at x goes to 0 of 2x minus 4. The expression 2x minus 4 is already in the closed form. And the function f of x equal to x minus 4 is continuous everywhere. It is a linear function. And so to find the limit, we simply evaluate the function. 2 times 0 minus 4, which is negative 2. And so the limit is negative 2. For the second part, the function is also in the closed form. However, if we plug in negative 2 into this expression, we will get 0 over 0. As of now, we are not going to use the L'Hopital rule, but we will try to factor both numerator and denominators. The limit at x goes to negative 2. The numerator is the sum of 2 cubes because 8 is 2 cubed. And so x cubed plus 8 is x cubed plus 2 cubed. And so in the numerator, we have 8 cubed plus b cubed. And again, it is the sum of 2 cubed. And the sum of 2 cubed can be factors as a plus b, where a is x and b is 2, a plus b, times a squared minus ab plus b squared, where a is x, so a squared is x squared minus, not plus, but minus ab, a is x and b is 2, x times 2 is 2x plus b squared, b is 2, 2 squared is 4. In the denominator, we have a trinomial which can be factors as x plus 2 times x plus 1. We can check that x times x is x squared, x times 1 is x, 2 times x is 2x, 1x plus 2x is 3x, and 2 times 1 is 2. We can cancel out the factor x plus 2 and x plus 2 in the numerator and denominators. We have a new limit problem. The limit at x goes to negative 2 of x squared minus 2x plus 4 over x plus 1. We will need to keep writing the limit notation here because we will still have x in the expression. With this new limit problem, we evaluate the limit by simply plugged negative 2 into x again to see what happened. If we plug in negative 2, we'll have negative 2 squared minus 2 times negative 2 plus 4 over negative 2 plus 1. In this case, everywhere we see an x, we simply plugged in negative 2. Substitute x with negative 2. X is a placeholder. Negative 2, the quantity square is positive 4. Negative 2 times negative 2 is 4, so 4 plus 4 plus 4 is 12 in the numerator. In the denominator, negative 2 plus 1 is negative 1. 12 over negative 1 is negative 12. And so the limit is negative 12. Notice that we dropped the limit notation at this point because x is no longer in the expression. Part C. The limit at x goes to 0 on the left-hand side of 1 over x squared minus x. If we plug in 0, then we will get 0 minus 0 in the denominator, which for now it is indeterminate. And so a clever trick in this case is to factor out x in the denominator. We obtained a new limit. The limit at x goes to 0 on the left-hand side of 1 over x times the quantity x minus 1. Not so much as a new limit, but a different looking expression that is the same as the given problem. And the reason why we do this is because 0 minus 0 is not defined or indeterminate for now. If we plug in a number on the left-hand side of 0, such as negative 0.00001 into this expression, then we will get 1 over negative 0.00001 times negative 0.00001 minus 1. And the numerator is a finite number 1 over the denominator is, remember, when x goes to 0 on the left, we use negative 0.00001 to indicate a very small negative number, but it's not quite this finite number. And so we go back to using the notation very small negative number times negative 0.00001 minus 1 is a number that is very close to negative 1.00001. Now, if we have a very small number times negative 1, almost negative 1, then we will end up with a very small number still. And a negative number times a negative number is a positive number. And so in the denominator, we still end up with a very small number, but it now is positive. A finite number 1 over a very small number is a very large number, and we indicate the very large number positive using the positive infinity. And so the limit for this is positive infinity. Remember that infinity is not a finite number. We're saying that the limit does not exist in a special way in this case, which means at x goes to 0 from the left-hand side, this function increases without bound. And the notation for increasing without bound is positive infinity. For part D, the limit at x goes to 4 of x minus 4 over the square root of x minus 2. If we plug 4 into this closed form, we will get 0 over 0, which is indeterminate. And again, we are not using the L'Hopital rule yet. One way to do this is to factor the numerator and see if we can cancel out any common factor. X minus 4 can be rewritten as the square root of x squared minus 2 squared, which is the difference of 2 squared, a squared minus b squared. And so we have the limit at x goes to 4. In the numerator, we can factor this as the square root of x plus 2 times the square root of x minus 2. The difference of 2 squared is the product of the conjugate. The denominator is the square root of x minus 2. And we see that we can cancel out the square root of x minus 2. We're left with the limit at x goes to 4 of the square root of x plus 2. We plugged 4 into this closed form to get the square root of 4 plus 2, which is 2 plus 2, or 4. And again, notice that we drop the limit notation when we evaluate the closed form. And so the answer is 4 for part D. Now we factored the numerator, but an alternative way is to multiply the conjugates, both numerator and the denominator, and the conjugates of the square root of x minus 2 is the square root of x plus 2. We will end up with the same result.